Now I'm
You
recording.
are now recording.
Now I'm recording.
Whoa. I didn't get anywhere.
Stop ready.
Okay, I'm not sure. Oh, I know what I did. Yeah, I know I did this. Okay, I got it. Now I remember. I had to think why. I chose these all very carefully. Okay, what am I going to do with this one?
You're gonna maybe move the 2 over, move the 10.
Move 2 over. Okay, so we get x squared minus 2x plus 1 equals 0. Magic numbers. Good. What would they be?
Negative 1, negative 1.
Negative 1, negative 1. So that's x minus 1 squared, isn't it?
This is just like a squared.
Equals 0, right? We didn't have to complete the square because it already was a square, right? And so what are my solutions here?
So then it's like 1 plus or minus 2 minus 1.
So it's x equals 1. That's it, right?
That makes a lot. That's actually.
Okay, but that seems to have violated our first rule, right? Look at our fundamental theorem of algebra. Every polynomial function of degree greater than 1 has exactly n zeros if the degree of the polynomial is n. Well, what's the degree of that polynomial? 2, right? We can see that the degree
Greater than 1.
equals 2. How many zeros did I get?
0.
I got 1.
1 0.
What's the problem?
You didn't do it right.
I did it right.
Can't you do 0?
Okay, yeah, so here's the deal. So the multiplicity of that 0 is 2, right? When I said x minus 1 squared is really x minus 1 times x minus 1, right? So I get the 2 zeros, x equals 1, and x equals 1, right? So that counts as 2. It counts as 2 because it shows up twice. And so I would say here that because that factor is being squared, the multiplicity equals 2, right, of that factor. Okay, and it shows up. As you might expect, it shows up as a different looking 0 than the others did. If we look back at all these other pictures that we drew where we had zeros, each of these x-intercepts, or these real zeros, showed up as a place where the function crossed through the x-axis, right? Okay, why is that? If I were to, here's a good way to think about this, and this is I want you to really kind of use your imagination a little bit. This is a topic that wouldn't show up in a normal high school math book, right? But it's something that'll still help you, if you kind of get this internalized a little bit. If I were to zoom in infinitely far on either one of those two solutions, what would the curve start to look like? It would look like a line, wouldn't it? Right? So these are linear solutions because they cut through the x-axis like a line does.
Well,
Okay.
what if it's just on the x?
Okay, exactly.
Is that what that was?
Aha, so what do you know? There it is, right? Very good. So when the multiplicity is 2, notice that the function doesn't just cross through the x-axis like a line, it acts like a parabola, doesn't it? Right? It looks like the vertex of a parabola. And so a lot of times we'll describe this in math, talk about bouncing, right? That's a 0 where the function bounces from the x-axis. So it's because it's quadratic, right? It's got a multiplicity of 2. Okay? What do you think? And I'm just throwing this out there. We'll come back to this and talk in more detail about it later. But what if I had something like, for example, what if I were to graph the function, say when in factored form it was x minus 1 cubed equals 0. What do you think it's going to do at 1? Okay, it's probably not going to cut straight through like a line, but it's also not going to bounce like a parabola. What does a cubic function look like? And we haven't looked at our toolkit of functions in a long time. We'll do that soon. But it's the one that comes down like this, right? It's going to come down, and it's going to be parallel to the x-axis where it crosses, right? But it's going to pass through on the other side, just like a cubic function does. Okay, so we can see then, And we'll get this, whenever we look at the zeros of a function, you can tell by inspecting it. And that's one of the things I want to do with you guys, and I won't normally do, is I want you to be able to look at a function and kind of guess what the behavior of the function is based on just the way the graph looks, right? So we could look at a function that does this and know, aha, we know that we're getting, that's going to have a multiplicity of 2. Or it could be, you can't tell always for sure, because a quartic function, if it's a 4th degree polynomial, it looks kind of the same, remember, but it just gets flattened out a little bit. See what I'm saying? If it's a 6th degree, it just gets a little bit flatter. So you'd know that you have an even multiplicity if the function bounces at that x-intercept. And you're going to have an odd multiplicity if it's what we call in calculus a point of inflection. It's a place where it flattens out and then curves back down again. Okay? That makes sense? Just, that's not the point of today's talk. I just want to throw that out there for later discussion, let's say. All right, so what about one like this? Let's solve this guy. What did we say we did with, now this is a cubic function, right? It's not quadratic, but maybe we could try to extend our thinking from quadratic functions. What would we have done back in Unit 2 with this one? What would we do there, do you think? Isolate x. We can point to a single x, so we isolate it. Okay. So what would the 2 steps be to isolate x this time? And this is some new stuff. We haven't really talked about radicals yet, right? And taking roots other than square roots. We'll get there. That's coming up. But we'll just kind of cheat a little bit now and try that. So I'd add 8 probably, right? And then what? Say it again. Cube root it. If I cube root both sides, if you take an odd root, you don't get a plus or minus. You just get one answer. And so what's my answer? 2. Okay. Good. And if I look at the result, sure enough, you can see that, what do you know? I do get a real 0 at 2. Okay, but what's wrong with that result? Look at that picture based on the discussion we just had. Look at the nature of that x-intercept and the degree of that polynomial and the number of zeros I got. What's wrong? I only got 1 0. How many are guaranteed that I should have? 3. Okay, well, does this one have a multiplicity of 3, do you think, based on the graph?
Yes.
But we said if it has a multiplicity of 2, at the x-intercept it would have to bounce off like a parabola. And if it had a multiplicity of 3, at the x-intercept it would have to be an inflection point where it's gonna graze the x-axis and then curve back down again, right? Is it doing that? No, that looks an awful lot like a multiplicity of 1, doesn't it? It just cuts right through the x-axis, and it is. So something's wrong with this picture then, right? We lost 2 complex zeros, right? So there's a moral to this story. It's not this easy, right? If we want to find all of the complex zeros, not just the real ones, and I know that we have a strong bias towards the real solutions because we use real numbers a lot more in our everyday lives than we do imaginary numbers, right? But once you get into real math, like using real math in engineering or in physics or in mathematics, you start to realize that that's a bad bias, that the imaginary numbers are just as important as the other ones, and we need those too, right? They show up a lot in lots of applications too, right? So we got to be able to find those. So something's wrong with this. Isolating x didn't work. We lost 2 zeros. It worked for quadratics, fine, that's okay, but it didn't work for stuff that was higher than quadratics. So we gotta go to something a little different. Okay, we're gonna go to some patterns, some factoring patterns that are gonna allow us to recover those lost zeros. Okay. Well, the factoring patterns for sums and differences of squares are pretty straightforward, right? A squared plus b squared, there's no pattern. It equals a squared plus b squared. Okay, nothing comes out of that. It's very useful. It doesn't factor. Okay. What about a squared minus b squared? That one we know. What does the difference of squares always factor into? Do you remember? We haven't officially talked about it, but we've used it before.
A plus B.
Part of it. Like you could tell me right now, if I had, for example, what's it going to be?
A plus B.
Times a minus b. There you go. It's the conjugate pattern, right? And that's one you may have been familiar with. If not, now I expect you to be familiar with it. If you weren't up until now it's one we're going to use, right? So there's our 2 the sums and differences of squares patterns. Only one of them is an actual pattern, the other one is no pattern. What about sums and differences of cubes? Okay, what I want to show you with this is, there's a way to remember this where you'll kind of hang on to it a little bit longer. You can see the pattern better if you look at it this way, right? So if I have either a plus sign or a minus sign there, meaning a sum of two cubes or a difference of two cubes, things that are being cubed is what I mean when I say cubes. Here's the pattern. Whatever shows up here is automatically going to end up there, right? Then it's going to alternate. From there, whatever this one is, that one's going to be the opposite. And the last one is always
The same.
plus. Always plus every time. Okay, last one's always plus. So, for example, if this is a plus sign, that's a plus sign, and that's a minus sign, right? Guaranteed.
But how do we know the whole, just gotta memorize the.
Oh, okay, and the other stuff, yeah, what about the other stuff? So the other part, so let's go back. No, those are just there to, they're just there to cover up the signs. Okay, how about the other, what about the powers? So if we have a sum or difference of cubes, it's always gonna factor into a small linear factor, where the first term is a and the second term is b, and a big quadratic factor, where the first term is a squared, last term is b squared, and the middle term is the product of a and b. Now, don't confuse this with, oftentimes people do this, don't confuse this with the pattern a plus b squared equals what?
A squared plus 2ab.
That's totally different stuff, right? That's what we call an expansion pattern. If we're taking an a plus b to a power, these are our patterns for what are we going to get when we multiply it all out. Very different stuff than what we're doing here. These are factoring patterns. We're starting with already something where we have some squares in it or cubes in it, and we want to break it up, we want to split it apart into a product of small factors, right? So don't confuse those two. Okay, so we got these two patterns. Come on. There. Okay, and I think I can, yeah, there we go. So there they both are, right? But if you get one, you get the other one, right? I mean, they go together, okay? So now let's see what happens if we use these patterns to solve that last equation. So let's start again. X cubed minus 8. Now let's not isolate x. Let's think about this as one of our patterns. Well, what's the only pattern that one could fit? All we have is a difference of squares, or a sum or a difference of cubes. Which one's that going to be?
The very last one.
Okay, the difference of cubes, right?
Yeah.
Difference of cubes. So for this to work then, I've got to be able to write this in the form a cubed minus b cubed, right? So what's my a?
The one.
No.
X.
X. What's my b?
0.
No.
Eight.
But what is 8 is what cubed?
Oh.
2.
Oh.
See what I'm saying?
Oh.
Okay, see the pattern? So then now we'll just follow the pattern. So you tell me real quick, what's the pattern for a difference of cubes?
A minus b.
A minus b times
A squared
plus,
AB minus.
no, last one's always plus, right?
B squared.
Plus b squared. So if we plug in our stuff then, a you told me was x, b you told me was 2, so a squared becomes x squared, ab becomes 2x,
Plus.
b squared becomes 4, right? Okay, and this whole thing, remember, is just equal to 0. Okay, that's great. Now look, we've got an equation in factored form. Okay,
They didn't think of it this.
right? So what do we do after we factored an equation? What do we always do?
Oh,
It's a good start.
it's true.
Now, what do we do? The whole point of us factoring stuff back in Unit 2 was so we could apply the, what's that property? Zero product property.
Ah.
Right? So we can apply the zero product property. Once we get it down to a small enough place, we can apply the zero product property and just set each of the factors equal to 0, right? Well, what does it mean to be a small enough place? When do you know, so when we get into some bigger problems, I'll kind of talk about it as when you bail off the factoring train, right? I mean, you factor as much as you need to, but then at some point, you're done factoring. You don't have to anymore. When are you done factoring? When it's, well, when it's convenient sometimes, but you always have to get these factors down to be quadratics, don't you? Because we know how to solve quadratic equations. If I set this factor equal to 0, the answer's pretty obvious, right? If I set x minus 2 equal to 0, I get x equals 2, right? What if I set this factor equal to 0? Okay, it may not be as obvious, but 100% certain we can do that because it's a quadratic equation in standard form. There is no quadratic equation in standard form that we can't solve. We can always default to using what? Quadratic formula. We're always going to get solutions from this, right? If we choose not to do something else like complete the square, we can always do the quadratic formula, right? So let's just do it here. If we apply the quadratic formula, we're going to get x equals negative b plus or minus the square root of b squared minus 4 times 1 times 4 is 16, right?
Yes.
All divided by 2 times 1 is 2, right? So if we just simplify that, we get x equals, let's break this into two parts, right? So I'm getting negative 2 over 2 plus or minus the square root of negative 12, right? All that's just going to become, isn't all that stuff in there just going to become a negative 12?
Yeah.
What's the square root of negative 12?
Something I.
So I'm going to get an I, right? Because I've got the negative there, I know I'm going to get an I at the end.
Isn't it like 3 radical 3i?
So the square root of 12, I can break that up into the square root of 3 and the square root of 4. The square root of 4 is 2, right? So I'm going to get 2 radical 3 over 2. And that works out a little bit better. I end up with x equals negative 1 plus or minus the square root of 3 times I. Okay. So how many total zeros did we end up getting? We got 3. We got our one real 0 that corresponded to that linear x-intercept, right? Multiplicity 1. And then we got these 2 other zeros that were a complex conjugate pair.
That's
Right.
real math right there.
That's real math, right? So, what should you expect then when you're doing this difference of cubes or sum of cubes pattern? This is only one example, but it's exemplary of all the examples we could do. If we try to solve this thing, what we're going to find is it's always going to give us i's. It's always going to be what we call an irreducible quadratic factor. So we're always going to get 2 complex solutions out of this. We're only ever going to get one real solution. So just know, like if we're looking for real zeros only, sometimes we are. Sometimes we want to only find the real zeros. I would never have to even think about this one right here. I know I'm going to get i's out of that one. This is the only real solution I'm going to get. Okay? Question?
So the equation has like the diff on the 0 factor, when you go for the i's, just come out to 0?
So you're talking about right there?
If that little part there is on the x-axis, what does it look like?
Then it wouldn't be, then that would be multiplicity of 3, right? See what I'm saying? Like we took an example, didn't I? We drew one right here, right? We had x minus 1 cubed. So there's where that little diff is on the x-axis, but then we know it counts, it has 3 real zeros, all 3 of them are right there, it has a multiplicity of 3. There are no real zeros to that one, are there? The only 0 is, by the zero product property, is 1. I get 3 zeros, x equals 1, x equals 1, x equals 1, for each of those 3 factors, right?
So if we took the equation like that and put it into the equation that we were doing earlier, what happens?
I'm not understanding what you're saying.
Go over to
Like that one?
yeah, if we do a problem where it has 3 real zeros, what does it look like in that equation?
Where it have 3 real zeros, it would look like this. It looks something like, I don't want that there, I don't like that there. It would look like this. 3 real zeros would just look like this. Okay, that's a cubic too, but it's just got all real zeros. Okay, all different real zeros.
I guess, I think what he's asking is, if you solve that with the equation, what result?
No, it wouldn't come up that way, because, I see what you're saying. A function like this is never gonna be in the form of a difference of cubes. Okay,
Oh, it'll be.
it'll be a different form, yeah.
Oh, so
Different.
just A minus B plus AB is gonna
Right, anything that's in the form, difference of cubes, where you're solving for x, you're guaranteed you're getting one real zero every time, that's it. Okay? All right, so, what about something like, well, we can skip that, that's easy. What about something like, oh, I mean, that's, well, what would you do there to solve for x? Let's just look at this one, I guess.
Just move the 2,000 over there. Whatever. 2,000.
So 54, I don't think divides evenly into 2,000. Try it. I don't think it does.
No.
Okay. So this is a good one to do. What are we going to do here?
Subtract 2,000.
Subtract 2,000. Okay.
And then cube root it, or turn it into cube, whatever.
Okay, if I were to just cube root it, I'm only going to get the real zero. What if I want all the complex zeros? I got to put it in that form. So what could I do to simplify this equation here? Divide by 2. Divide both sides by 2, right? And that's going to give us 27x cubed minus 1,000 equals 0. Okay, that was helpful because those numbers ought to seem a little better in terms of the pattern we've got. What's the only binomial factoring factor? Binomial, because I've only got 2 terms, right? What's the only binomial factoring pattern that could apply here?
The cube minus.
Well, the difference of cubes, right?
Yeah.
So this has got to fit into the form a cubed minus b cubed, right?
Yeah.
Well, by b is pretty easy. It's cube root of 1,000.
Yeah.
Yep.
Yeah.
Okay, what about a?
3x.
3x, right? Because 3 cubed is 27 and x cubed is x cubed, right? So now we could just follow our pattern. We know that we're going to get a minus b times a squared
B
plus ab plus b squared, right? You get that? And so now we'd have to, if we want to simplify that, that's just going to look like, well, this one's done, 3x minus 10. What's 3x quantity squared?
27.
No.
Oh.
9x squared, properties of exponents, right? I
Yeah.
would just distribute the 2 to both factors. I'd get 9x squared plus 30x.
100. Wait, but shouldn't there be parentheses around the 27x cubed up there? The very start. There doesn't have to be?
No.
Why do you have the cube root of 27 if it's?
Well, because, I mean, I don't need parentheses there because the 27 is being multiplied by the x cubed, right? But in order for us to factor this, we have to be able to rewrite that first term as something cubed, right? As the quantity something cubed, and the quantity is 3x. What would I cube to get the term 27x cubed? I would cube the quantity 3x, okay? So how many real zeros are we going to get? One. And what is it?
Like a number that's.
What is it? If I set that equal to 0 and solve, what am I going to get? Well, but I want, this is a fraction.
Yeah, so I don't know.
10/3, right? So I'm going to get x equals 10/3, or I know here I'm going to get a complex conjugate pair of solutions that have i's in them, right? Have imaginary parts. Okay? All right, so what about something like that? How much time we got?
1 minute.
Oh my gosh.
16 is the cube root.
I like your shirt.
Thank you.
I like my shirt too.
Okay, we'll pick this up tomorrow.